All right, here we are at 3-5, which is our last learning objective in the momentum unit. This one is going to be talking about a really fun thing called an MVP chart. And I'm not being sarcastic. It's actually like my favorite thing in this whole unit. And a lot of students actually end up finding that once they figure it out, it's kind of fun, sort of like a crossword puzzle or a Sudoku puzzle or something like that. That might not be you, but hey, it might be. You might actually really like this stuff. So an MVP chart is a tool that we use to calculate the initial velocity, or the final velocity, or possibly the mass of an object in an inelastic collision or explosion. It can also work for an elastic collision, but just know that the learning objective only includes inelastic collisions, at least for the test. We'll do a little bit of elastic though, just to keep things spicy. All right, there are two types of collisions that we need to know for right now. The first one is an elastic collision. And the second is an inelastic collision. Now, you've seen that word elastic before. You think of it and it means to you something like stretchy. But it also kind of means bouncy. And so for our definition, think about elastic as sort of bouncy or rubbery. An elastic collision is a collision where the two objects bounce off of each other and remain separate after the collision, whereas an inelastic collision is one where the two objects stick together and remain together after the collision. All right, people, let's use this example right here. We've got a bouncy ball here on the left, and it hits the ground, and it bounces back up. They do not stay together. That is an elastic collision. On the other hand, to the right, we have a piece of clay. And when clay hits the ground, it doesn't bounce. It goes splat, and it just sticks to the ground. That is an inelastic collision. Now, all right, in the real world, this is actually a spectrum. All collisions involve a little bit of bounce and a little bit of splat. So if you have the crash between two cars, it is mostly inelastic, but the cars don't actually stick together. They kind of bounce off of each other a little bit. Whereas if you have a foot hitting a soccer ball, that is mostly elastic. They definitely separate, but there's a little bit of splatting, a little bit of squishing going on in the soccer ball. So really everything is somewhere on that spectrum. But in physics, we just kind of decide, all right, well, there's elastic and there's inelastic, and we try to keep them separate just to keep things a little bit simpler. An MVP chart is a tool for looking at these collisions. Okay, so here's the rules for an MVP chart. Each column of the chart, I'll just show you what it looks like real quick. It has columns and it has rows. Each column of the chart is found with this equation, P equals M times V. We know that the P in this equation is momentum, that M is mass, and that V is velocity. The mass row, which is this first row right here, highlight M off to the side. The MVP stands for mass, velocity, and momentum. So the mass row is found with a rule called the law of conservation of mass, which tells us that the mass before and after an interaction is always equal. Total mass before and after must be, we could say, constant. Okay, so in the mass row, the total mass before, total mass after is going to be equal. Okay, the momentum row is found with conservation of momentum. Which tells us that the total momentum before and after must be constant. So on the momentum row, it's going to be the same before and after. The last thing we need to know is that the V in MVP, which stands for velocity, is not conserved. So there is no conservation of velocity. Now, we wrote down a whole bunch of stuff there, but and we highlighted a whole bunch of things, but I've combined it together in a handy little chart right here that tells you things that are conserved, mass and momentum, and things that ain't. All right, let's look at our MVP charts. So let's say we had this problem. We have over here in the left, we have our before picture. So we have a 4 kilogram cart moving at 5 meters per second, and we have a 1 kilogram cart that's not moving. And we're going to draw an after picture. Now this is an inelastic collision because the two carts stick together, and we want to know how fast they're moving. All right. Now in that picture, we're going to use the information to fill out the rest of our MVP chart. Remember that M, V, and P are each rows of the chart. So the first row is mass, the second is velocity, and the third is P, which stands for momentum. All right, let's fill in everything we know. So looking at the picture, we can see that this cart is 4 kilograms, this is 1 kilogram, and then over here, they're going to be stuck together. Okay, so I'm going to do 4 kg and 1 kg. Notice I'm filling out the space below the cart. Okay, now over here, what we're going to do is something kind of tricky because this is an inelastic collision. We're going to treat them as the same object. So we're going to see that this is not 4 kilograms and 1 kilogram. It's just 1 5 kilogram object. So much easier that way. All right. Now the other thing we know is we know the velocities. So this is moving at 5 meters per second. This is moving at 0. And we're trying to solve for the velocity over here. So what I'm going to write is 5 meters per second, 0 meters per second, and then a question mark, because that's what I'm trying to solve for. And I'll erase that later. Okay. Now that we have all of that figured out, the next thing we need to think about is how we solve for things in columns. And so we've got this whole thing that we filled out here. The first piece of advice, right there, is that each column is found with the equation momentum equals mass times velocity. So we can take the mass row and multiply it by the velocity row to get the momentum. So 4 times 5 equals 20 kilogram meters per second. 1 times 0 equals 0 kilogram meters per second. Whatever. And then 5 times question mark, we don't know. It's something. Okay? That's how we go down the columns. The next thing we need to do, let's go back to our instructions up here, is we need to look at the rows. So the mass row is found using conservation of mass. So 4 kilograms plus 1 kilogram would have to equal 5 kilograms. We have to have the same momentum or the same mass before and after. Okay, and we do. Our next rule is that the momentum row must be found with conservation of momentum. So 20 plus 0 should equal the momentum on the other side. If I have 20 momentum at the beginning, I'm going to have 20 momentum at the end. And just to make my life easier, I'm just going to copy it and paste it over here. Okay. So there we go. We have conservation of momentum now. All right, let's go back to my instructions. The last instruction is there is no conservation of velocity. So for the middle row, I don't add those up In fact, they're not equal. I'm going to put a little not equal sign right there. All right, so I've filled out as much of my chart as I can at this point, and I got to do some thinking. I'm still missing the velocity. But remember, the first thing we did was we said that mass times velocity equals momentum. So if I go over here, I can use that equation. I'm just going to write it like this. Momentum equals mass times velocity. Well, I know the mass is 5, so I can plug that in. And I know the momentum is 20, so I can plug that in. And now I just can solve for the velocity. So the way I do this is I've got to get I've got to get like velocity by itself. So I'm going to divide both sides by 5. 5 cancels out on the right-hand side. 20 divided by 5 is 4. And that is my velocity. And I'm going to take that and plug it in right here. So hopefully you can see that MVP charts, they're kind of like this puzzle. You have to know the rules, where you add, where you multiply.